Welcome to video 2 of the Omnia II video series. During the course of this video, we're going to show you how to set up tests on your instrument and run tests, as well as getting test results. First, we're going to show you how to set up and save a test file. That way, you'll be able to add the necessary sequence and associate it with a file name. From the main menu, press the Setup Test soft key. From the Setup Test screen, press the File soft key. From here, you have 5 options: New File, Save, Save As, Delete, and Load. We want to create a new file. Select New File and use the alphanumeric keypad to put in the file name. Should you make a mistake, use the back key to delete a character. Turning caps lock on will allow you to hit in only capital letters. You can also use the symbol key to toggle between various symbols. Once completed, hit Enter to accept your file name. This will take you to the Setup Test screen. As you can see, the bottom of the screen shows the file number, 5 in this case, and the file name. If you wish to rename your file, select the file you wish to rename using the arrow keys, and select the Save As soft key to rename the file. Either hit Exit or Enter to save your choice. If you wish to delete a file, use the arrow keys to select the file you wish to delete and simply hit the Delete soft key. It will ask you if you're sure you want to delete. Press Exit to cancel or not delete the file, and Enter to delete the file. To load a file, simply use the arrow keys to select the file you wish to load and press the Load soft key. This will automatically take you to the Setup Test screen, showing you all the tests you currently have in this sequence. Now that you know how to create a file, we're going to walk through how to set up each type of test, as well as provide a description of the test parameters. We'll first walk through setting up a dielectric withstand test, then an insulation resistance test. After that, we'll go through AC ground bond and DC continuity tests. Finally, we'll walk through how to set up functional run and line leakage tests. First, we're going to add a dielectric withstand test. Hit the Add soft key, and you're going to have several choices of the type of test you'd like to add: dielectric withstand, insulation resistance, AC ground bond, DC continuity, run test, and line leakage test. First, we're going to select dielectric withstand, and it gives us the choice of either an AC test or a DC test. For the purposes of this demonstration, we're going to select an AC withstand test. The first parameter is the set voltage. For the purposes of this demo, we will simply use 1200 volts as our test voltage. Next parameter is our total high limit. This is the absolute maximum amount of leakage current that is allowable before the test would fail. The total current refers to both the capacitive and resistive elements of the leakage current. You'll note at the bottom of the display that for each parameter it gives you the range of the parameter. So in this case, I could set my high limit total all the way up to 100 milliamps. The low limit actually gives you a bottom portion of the window to make sure that your leakage current does not drop below a certain value. This is very handy, especially in a case where you might not have the return lead connected. In that case, the unit will register 0 leakage current, but you're really not testing your product. Your ramp up time is the amount of time it takes to get from 0 volts to full voltage. The ramping up is linear. For example, if you set 5000 volts with a ramp up of 5 seconds, the unit will ramp up 1000 volts per second. The dwell time is the amount of time at which the unit holds full voltage for your testing. This is essentially your test time. The ramp down time is how much time it takes the unit to get from full output voltage, or your voltage setting, back down to 0 volts. Just as with the ramp up, the ramp down is also linear. Next is the arc sense. Arc sense and arc detection are a special feature on the Associated Research Inc. units. What it allows you to do is detect the buildup of corona or high frequency noise as a high pot test is occurring. In order for arc detection to work, you need to turn arc detect on. Otherwise, the arc sense value means nothing. You can set the arc sense from 1 to 9, 9 being the most sensitive and 1 being the least sensitive. Keep in mind that arc detection is generally not used as a pass-fail criteria, but more for quality control. There are 2 additional parameters for monitoring leakage current windows. That's high limit reel and low limit reel. The Omnia unit actually has the capability to calculate the real or resistive portion of the leakage current during an AC withstand test. As you can see, the high and low limit reel give you the same range as the high and low limit total for which to set a window. The offset parameter actually allows you to offset any parasitic capacitance that might exist on the setup due to test fixturing or the unit itself. Using the offset feature is very easy. All you need to do is set up your test fixturing. I have the adapter box and a lead connected right now, and then push the test button so that the unit can automatically get a value. In this case, my value is very low, only about 3 microamps. But in other cases, you might get much more depending on how much cabling you have coming from your unit. Pressing more will take you to the next set of parameters. As you can see, there's another set on the right-hand side of the screen. The continuity parameter actually allows you to run a brief continuity test prior to the high pot test to make sure that your return and ground pin are connected to the product. The DUT output is a special feature on the Omnia unit that allows you to output voltage and current from the rear panel, line, neutral, and ground connections. This comes in handy when using an Omnia 8206, 7, 56, or 57 because it allows you to connect your product and run it all in one setup. For the purposes of this demonstration, since I'm going to be using the line, neutral, and ground outputs, I'm going to leave DUT output on. The Omnia also gives you the capability to select your meters and how you want your meters displayed on the LCD. For example, you can see that I have light blue selected as voltage. This means that voltage will be my top parameter in the middle of the screen, where total leakage current will be the dark blue on the bottom, and I can rearrange these any way I see fit. Should you want to set all of your test parameters back to factory defaults, simply hit the default soft key. You'll see all the parameters highlighted and push enter to accept. Pushing exit will take you back to the setup test screen, and you can see we have our AC high pot test. Next, scroll down to the next available step, which is step 2, so we can add another test. Next, we're going to add a DC high pot test. Hitting the add soft key, I once again select dielectric withstand, but this time select DC withstand. As with the AC withstand test, you're going to see a lot of the same parameters. For example, the voltage is simply the voltage output of the unit. I'm going to select 1500 volts and hit enter to accept that value. Also, as with the AC high pot test, we have a high and low limit value. What you'll notice here that is a bit different than the AC test is that the DC test is specified in microamps rather than milliamps. That's because the leakage current for a DC test tends to be much lower. Remember, when we're running a high pot test, we're really dealing with a capacitor because we're testing the insulation on a product. So with a DC test, once the product is charged, you're going to have very low levels of leakage current. Same as with the AC test, you have a ramp up, dwell, and ramp down timer. Since we're dealing with the DC withstand test, and I could have some inrush current, I'm going to increase my ramp up time to 2 seconds. One of the unique parameters for a DC withstand test is the charge low parameter. As I just previously mentioned, once the capacitance of your DUT is fully charged, you're going to have very little, if any, leakage current. That being said, it can be difficult to set a low limit because you might not have enough for the low limit to register. And you always want to make sure that your product is properly connected. If your return lead happens to fall off mid-test, or fall off at the beginning of the test sequence, you want to make sure that you're actually running your test, and you want the unit to give you a warning. Well, the charge low parameter does just that. What it does is it looks at half the charging current during the beginning of the test, and then sets that to make sure that you actually have something connected. The charge low parameter depends on 3 factors. Number 1, the voltage level, as a higher voltage is going to give you a larger inrush current. Number 2, your ramp up time. as a shorter ramp-up time will mean a larger current spike, and then number 3, the DUT itself. Right now, I have a small capacitor connected to my unit. If I want to set the charge low value, I simply need to have all my parameters set as I want them, and then have my DUT connected up just as I would if I were testing. I simply need to push the test button and it will automatically take a reading. In this case, 14.7 microamps, which means the total charging current was about 28 microamps. Just as with the AC test as well, you can offset a value. So if I wanted to offset my lead fixturing, I could. The DC withstand test also has a couple other features that are not available on any other test type. The first one is the ramp high feature. The ramp high feature can be toggled on or off. With ramp high on, the unit's going to ignore the leakage current during the ramp up phase. If you have a highly capacitive DUT, the charging current during the ramp up can be very severe. If your charging current exceeds your high limit during the ramp up, this can cause a false failure. So with ramp high on, it's going to ignore the charging current during the ramp up and only look at the current during the dwell time to make a determination on pass or fail. Next, we're going to add an insulation resistance test. The insulation resistance test is essentially a DC high pot test at a lower voltage. As you can see, you can only set the voltage from 30 to 1000 volts for an IR test. But instead of giving you a leakage current value, it's going to give you mega ohms or giga ohms of resistance to give you an actual insulation resistance value, hence the name of the test. This works in much the same fashion as the DC high pot test. You can set your voltage, your high and low limits, your ramp, dwell, and delay timers, your ramp down timer, and just as with the DC high pot test, the charge low parameter. A couple things I want to mention here. One thing you're going to notice is that you can turn your high limit off or to 0 as I have it here, which makes sense if you think about it, because the higher the insulation resistance value, the better. That's the same as having a very low leakage current. So I don't mind if it goes beyond the measurement capability of the unit as long as it doesn't drop below a certain value. Generally, the low limit is what you're looking at for an insulation resistance test. You don't want it to go below a certain value as called out for in certain standards. In this case, I'll set my low limit to 2 mega ohms. You'll also notice there's an additional timer on the insulation resistance test, and that's the delay time. The delay time occurs after the ramp up but before the dwell time, and it allows your leakage current to settle so that you can get a stable measurement before the dwell time kicks in and you make a determination on pass-fail. Your test will not fail during the delay time unless you have a direct short or breakdown on your product. For the purposes of this demonstration, I'm going to set the delay time at 2 seconds. As with the other tests, you can turn the DUT output on or off, or set the product test to defaults. I'm going to hit the exit key to go back and review the 3 types of tests I have just set. As you can see, there are only 4 parameters for a DC continuity test. DC continuity test is simply a low voltage, low amperage test that lets you know if you have a current path. This is generally used to make sure that the ground pin on a DUT is properly connected to the grounded chassis. Just as with the IR test, you have a high limit and a low limit that can be set anywhere from 0 to 10,000 ohms, or you can set it to 0 for off. The dwell time is simply the amount of time that the test is run. For the purposes of this demonstration, I have it set to 3 seconds. This unit also gives you the capability to do an offset. This is going to negate lead resistance when you're running a test. To perform the offset, simply short your current and return leads, highlight offset, and push the test button. The Omnia will get a reading for you. So 0.1 ohms will be negated from my value when I run this test. With those parameters set, I'm going to push exit and go back to the setup test screen. As step number 5, we're going to add an AC ground bond test. Similar to the continuity test, it's letting you know if you have a current path. However, this case, we're loading the circuit down with high amperage. This unit can output anywhere from 1 to 40 amps. You can also set the potential drop across the circuit. You're not setting the exact voltage drop, you're setting the voltage drop that it will not exceed across your circuit. For the purposes of this demo, I'm going to use 6 volts. We can also set high and low limits to make sure we don't exceed a value for resistance. For a ground bound test, generally the lower the value the better, because you want your safety ground to facilitate the operation of a safety circuit should there be an installation fault in the product. 100 milliohms is a very common high limit, so I'm going to use that. Low limit, I'm going to leave at 0, and I want to run the test for at least 5 to 10 seconds, or enough time to obtain a meaningful reading. Sometimes it can take a few seconds for the current to stabilize on an AC ground bond test. Just as with the continuity test, I can set a resistance offset value. I already have my lead shorted, so I'm going to push the test button and allow the unit to get a reading. So we can see our test leads have very low resistance, only 3 milliohms. Since this is an AC test, I can toggle between 50 and 60 hertz. Since I'm testing a product that's here in the States, I'm going to use 60 hertz. The Omnia II comes equipped with a new feature known as dual check. What dual check allows for is it allows you to run a simultaneous ground bond and high pot test to save on testing time. If I push the dual check soft key, it's going to give me 3 choices. First of all is off, in which case it's not being used, or I can run this ground bond test in tandem with a DC or AC high pot. If I select DC or AC high pot, my next test must be that same test type in order for this to function properly. You'll notice that when I tried to exit the step, it's warning me that dual check requires a corresponding dielectric withstand test to function properly. I can push enter to automatically add this dielectric withstand test. So if I add this test, this previous ground bond and this current AC high pot test will run at the exact same time. For the purpose of this demonstration, I'm going to leave the dual check on with this test to show how it operates. We now have 2 more types of tests to add. First is what's known as the functional run test. The run test allows a user to run their product at nominal voltage and measure various metrics, including current, leakage, power, and power factor. The functional run test is handy because it can catch defaults that an AC high pot test might not catch. For example, during an AC high pot test, you're shorting line to neutral, so you wouldn't catch a line to neutral fault. However, running a run test, you would catch such a fault. As you can see, there are several windows you can set as you're monitoring these metrics. You can set a voltage high and low limit to make sure it doesn't stray outside those values, an amperage high and low limit, a power high and low limit, as well as a power factor high and low limit. You'll notice there's also a leakage high and low limit. This test will also measure leakage current while the product is running. It uses a simple 2K ohm resistor to sense the current and give a measurement value. Since we're working with an 8257 unit, we also have a built-in AC power supply so that we can supply voltage for our functional run test. Hitting the AC source soft key will take me to a separate menu to set the internal 500 VA power supply. This product will run at 120 volts, so I'm going to set 120 and hit enter. The frequency will be 60 hertz, and I can choose to put a high limit window, but I'm going to leave that off. There's a couple of other options that you can set on the source. First of all, you can select whether you want a floating neutral or a grounded neutral. Open means the neutral is floating, whereas closed means it is grounded. You can also set your voltage range from low to high. Voltage range should be set low if you're setting your voltage under 150 volts. However, if you're going over 150 volts, you'll need to go to the high voltage range. This source also has a feature called OC foldback. OC foldback can be toggled on and off. The purpose of OC foldback is if you have a high inrush current when your product starts up, such as a motor. What it allows you to do is scale back the voltage to maintain a constant output current when the product is starting. As the current stabilizes, the voltage will rise back to nominal value. This is very handy because it allows you to start up products that would require a much larger power supply with only a 500 VA supply. Once all my AC source parameters are set, I can simply return to the run test parameters by selecting the run test soft key. The continuous parameter allows me to run consecutive functional run tests in a row without shutting down power to the DUT in between steps. This will only function if I have multiple functional run tests. For the purposes of this demo, I only have one functional run test, so I'm going to leave continuous off. There's also an optional parameter called PLC control. What this allows you to do is run an external power supply from Associated Power Technologies in the event that you need a source that's greater than 500 VA. Once I have all these parameters set, I'm going to hit exit and make sure that I have all the rest of my tests set. The last type of test we're going to add is the line leakage test. The line leakage test is a unique type of electrical safety test. Like a high pot test, you're measuring leakage current that's flowing through a product. That's where the similarities end. Unlike a high pot test, you're going to be running your product at its nominal voltage or at 110% of its nominal voltage and actually seeing how much leakage current results while the product is running. The other difference is how the leakage current is measured. For a high pot test, leakage current is generally measured by a current sensing resistor. For a line leakage test, we use what is called a human body impedance network or measuring device, which simulates the impedance of the human body to see how somebody would react were they hit with this type of leakage current and they're connected to the DUT. The first two parameters are your leakage windows. You have a leakage high limit window and a leakage low limit window. As you can see, this unit allows you to set anywhere from 0 microamps up to 10,000 microamps or 10 milliamps. For the purposes of this demonstration, I'll set this test at 5,000 microamp limit. I'll keep my low leakage limit to 0 microamps. The next windows are your voltage high and low limit windows. Generally, the safety standards call out for the exact amount of voltage that needs to be applied to the product. So it's important to closely monitor the voltage to make sure that your source is within range. For the purpose of this demonstration, I'm going to be running at 110% of 120 volts or 132 volts. I want to make sure that my voltage does not go above 136 volts and does not go below 128 volts. The next set of parameters are your timers. You'll notice for this test that you have two timers, a delay time and a dwell time. The dwell time is the amount of time at which the test is run. For the purpose of this demonstration, I'm going to set my dwell time for 5 seconds. However, you may need some time for your product to fully boot up before you want to take a leakage reading and determine whether it's a pass or a fail. That's what the delay time allows you to do, especially if you have a microprocessor-based device that takes some time to boot up. I'm going to set the delay time to 2 seconds. Finally, you have your offset parameter. The offset parameter, much like the offset on the AC high pot and DC high pot tests, allows you to offset any parasitic capacitance associated with the instrument. Simply connect up all of your fixturing without your DUT and push the test button. If you get a reading, this will be negated from your value. The other thing that distinguishes the line leakage test from any other type of electrical safety test are what we call fault conditions. The product is run at nominal voltage under these various fault conditions to give a worst case scenario of what could happen to somebody should these events occur while they're attached or touching the device under test. The first one is the neutral. Hitting the neutral soft key gives me a diagram of my line leakage testing circuit. You have two choices. You can either have the neutral closed, which is the normal condition, or open, which simulates an open neutral condition. I'm going to keep things under normal condition for the time being and have the neutral closed. As you can see, with the neutral closed, current will flow normally through the ground switch, bypassing the measuring device. The next fault condition is a polarity reversal. Select the reverse soft key, and once again, this will bring up the line leakage circuit. You can choose between having it off, which is normal condition, or on, which flips the polarity of the circuit. For the purposes of this demonstration, I'm going to keep normal conditions and keep reverse polarity off for the moment. Finally, we're going to go over the ground fault condition. Under normal conditions, your ground circuit should be closed. Pressing the ground soft key will bring up the circuit. As we can see, with my ground switch closed, the unit really shouldn't be reading any leakage current because the MD is outside this circuit. With ground closed, the MD is shorted out. However, once I do an open ground condition, the measuring device or the human body network now becomes part of the circuit, and your leakage readings are going to get much higher. For the purposes of this demo, I'm going to have the ground open so that we can show the measurements. So now we can see we have our neutral closed, our reverse off, and our ground open. With 3 fault conditions and 2 different settings for each fault condition, each line leakage test will have up to 8 steps if you're covering all cases. Next, we want to choose exactly how our circuit is being measured. Pressing the measuring device soft key will bring up the series of measuring devices that are built directly into the Omnia II unit. We have the measuring device for UL 544 non-patient, UL 544 patient, 60601 and 2601 medical device standard, 1563, IEC 60990 figure 4 U2, which is also the circuit for IEC 60950 on IT equipment, and then of course IEC 60990 figure 5 U3. There are also 2 additional selections. There's an external measuring device selection. The unit comes built in with an external measuring device PCB. This allows the user to populate a bare circuit board should they run into a measuring device that's not covered by the Omnia instrument. The frequency check is a unique selection on the unit that allows the unit to be configured to verify the bandwidth of the leakage current voltmeter by setting the probe configuration probe high to probe low and selecting frequency check. This selection is intended to meter verification purposes and has no application for normal testing. The calculation of the displayed leakage current will use a 1000 ohm resistor for R for the calculation of V over R equals I, where I is the leakage current displayed and V is the voltage across the measuring device. When an external frequency generator is applied to the probe inputs, the current display will be equal to the voltage generator over 1000. The readings can then be correlated to verify the voltmeter bandwidth. For the purposes of this demonstration, I'm going to select the medical device standard measuring device for 60601. Next is the probe configuration. The probe configuration is basically where you're placing the MD in the circuit. As we can see, there are 2 switches internally, switch high and switch low, which allow the MD to be placed in the proper position for measurement. Ground to line places the MD between ground and line reference on the circuit. This will be used for earth leakage measurements. Probe high to line places the unit between the output probe high and line for enclosure and patient leakage measurements. Probe high to probe low will place the MD between probe high and probe low terminals off the rear panel of the unit and will be used for patient-to-patient or mains on applied part leakage measurements. For the purposes of this demonstration, I'm going to do an earth leakage current measurement, so I'm going to select ground to line. Hitting the More soft key will take you to the next page of parameters. The leakage parameter determines whether you're going to measure leakage via RMS or peak measurement. RMS is very good for sinusoidal waveforms, but for waveforms that are non-sinusoidal, such as patient leakage or enclosure leakage measurements, you may want to use peak. For the purposes of the demonstration, I'm going to use RMS measurements. The continuous parameter is Associated Research Inc.'s active link feature. Setting continuous to on allows the DUT to remain powered up between all line leakage steps. This saves a great amount of time when testing line leakage, especially considering the number of line leakage tests you can have on any one single device, given the number of fault conditions and probing points. Just as with the functional run test, I can select the AC source for the line leakage test. I'm going to set it to 132 volts to do 110% of a 120 volt circuit, and I'm going to leave the rest of the parameters alone and go back to the line leakage test. The next parameter is the filtering circuit. On this Omnia II unit, you actually have the capability to measure composite leakage, filter DC only, or AC only. I'm going to select composite for the purposes of this demonstration, but you do have the capability to filter on this instrument. The ranging mode circuit allows you to select how you want the measurement circuit to range. Your choices are auto and manual. It is highly recommended you leave ranging mode to auto unless you have specific applications which would require manual ranging. Your PLC control, once again, is an optional control that works the same as it does in a functional run test, and your meter selection works the same as it does in the other tests with the different parameters specific to the line leakage test. Selecting more will take you back to your first page of parameters. Now that our test is set, I'm going to hit the exit key and make sure I have all of my required tests. Now we're going to make our connections to the DUT. First, I'm simply going to plug the 3-prong product into the adapter box. Next, I need to have a return point for my high pot ground bound and continuity tests, which will be the chassis point of the product here. Finally, for the line leakage test, I'm going to be doing one probing point on the enclosure of the device, so I'm going to connect probe high to the chassis as well. Now that our test sequence is completed and our product is connected, we're going to run this test sequence. I'm going to hit enter to get to the perform test screen. I'm going to use the arrow key to scroll back to step 1, and then I'm going to hit the test button to allow it to cycle through all of the tests. As we can see, all tests have passed. If I want to review the results, I simply hit the Results soft key, and I can use the arrow keys to scroll through each individual test to look at my measurements. Over the course of this video, we've shown you how to set up tests on your Omnia and run them as well as get test results. In the next video, we're going to show you how to use your Omnia II instrument in tandem with an Associated Research SC6540 scanner. Thanks again, and stay tuned for video 3.